Hello students, so continuing our lectures on electronic devices. So we will start with a diode today. Now diode, as you know, is a two-terminal device and it is mainly used as an rectifier. So it consists of a glass tube in which there is an so there is a glass tube. There is an anode sheet and there is a heated cathode. And this is the central heater. So as we have a diode which has two terminals, so you can call a PN junction as a solid state diode. So similar to diode, you can also have something called a triode, which has got three terminals. And apart from this anode and the cathode, as in the case of a diode, it has gotten a grid which is extra apart from the anode and the diode. It can be used as an amplifier or switch, and like in the case of junction, PN junction is a solid state diode, so a transistor can be called as a solid state triode. Now, bipolar junction transistors there are two types of transistors. One is junction field effect transistor and one is bipolar junction transistors, commonly called as BJT. So these transistors have got three parts to it. One is the emitter, one is the base, and the collector. So basically, if you highly doped the emitter, that is why it is written in N plus form, that means highly doped. You have the base P and you have the collector. This is an NPN BJT, and so this is the emitter, base, and collector. So this is where the emitter current enters from this terminal. Actually the other way around. It should be like this, and this is from where the collector current enters, and you have a base current entering from this side, and it is symbolically written as emitter, base, and collector. So the arrow is going outside, as in this case, as the emitter current. So this is an NPN BJT, and had it been the opposite, so had it been the PNP transistor, so highly doped emitter, N base, and P collector, then the collector current, emitter current would have been in this direction, IE, and this would have been the collector current, and the base current would have gone outside. So this is a PNP transistor, and its symbol would have looked like this. the current going inside, emitter current going inside, emitter, base and collector. So in an BJT we have three configurations. One is called the common base configuration, common collector configuration and common emitter configuration. Now there are some parameters associated with transistor. First of all, the total emitter current that is going inside or it is coming out is the sum of the collector current and the base current, and there is a quantity alpha and it is given as IC by IB. The common base configuration is used for power gain. It is when common base voltage is more than the base emitter voltage. Collector base voltage is more is greater than the, so you have emitter, base and collector. So when voltage in this part is more than the voltage drop in this part, you have a power gain. Then the collector power is greater than the emitter power. And the common emitter on the other hand is used as an amplifier or configuration used for amplification, and where the base current is amplified by collector. Apart from bipolar junction transistor, we have something called junction field effect transistor as well. So JFT are basically voltage control devices. And so they have mainly three sections to it. First of all is a source, in fact 4 sections: source, drain and a gate. So apart from that they have something called a channel. So this is your P, this is your source, this is your drain. So this happens to be the channel. So this is the gate, this is the source, this is the drain, and this portion is the channel. So here why is it called a gate, a voltage control device? That is because the gate voltage controls the current from source to drain through the channel. Gate voltage, it controls current from source to drain through the channel. And the width of the channel is controlled by the voltage applied to the gate. And secondly, the width of the channel is controlled by the voltage applied through the gate. So we have if you plot this is as the channel voltage, and we applied the base. So this is how you get, this is the VDS one, this is the base one. So for an N channel, the drain is positively biased, and the electron flows from source to drain, and at high voltages the saturation occurs at the drain side, and that is called the pinch off. Now drain current shows saturation with increasing drain voltage. So drain current shows saturation with increasing drain voltage. And the gate voltage reduces channel width and reduces the drain current, as when we apply gate voltage, it reduces channel width with increasing and reduces drain current. And when the gate voltage is extremely high, that means high gate voltage, destroys the channel, and we have zero drain current. So let us recapitulate. So whenever we are increasing the drain voltage, there has to be an increase in drain current till it gets saturation. Gate voltage, on the other hand, when we increase the gate voltage, it will reduce the channel width, and hence it will reduce the drain current. And if we increase the gate voltage, and so it will destroy the channel, and at least we get a zero drain current. So apart from junctional field effect transistors, we have another type of transistor which is called a Mosfet. Mosfet stands for metal oxide field effect transistor. and it is also a voltage control device. And the interesting thing about this is that the channel is not initially present as in the case of JFET, but the channel is created during device operation. So we have an NPN system. This is an N-channel Mosfet, and if we have a PNP system, we have a P-channel Mosfet. So basically you have an oxide layer, we have the source and the drain. So this is your SiO2 mainly, and this is, if this is P, this is N and N, so it becomes an N-channel Mosfet. If it is N and this is P and P, so it becomes a P-channel Mosfet. So if you look into the drain current and drain to source voltage characteristics of a Mosfet, so plot ID versus VDS. We'll write for 4 cases. So this will be the plot when the gate voltage is creates the channel for conduction. So here it applies the gate voltage, or let's call it as VG. It creates the channel for conduction, and this is the plot when the current flows from source to drain. Source to drain, there is a flow of current I. This is the point where the saturation is taking place. Current increases with drain voltage VDS until the saturation takes place. At high values of VDS, a pinch off occurs at the drain end. So it stops there and leads to saturation current. So the saturation current, it corresponds to the pinch off that is occurring at the drain end, the I sat. Now the gate voltage increases the channel width and increases drain current. And include that the gate voltage, it increases channel width, and increases drain current. This is somewhat different from what we have seen recently in the case of JFET. Here the gate voltage reduces the channel width and reduces the drain current. This is for JFET, but for the case of a Mosfet, it is doing exactly the opposite, increasing the channel width and increasing the drain current, opposite to what we have for JFET. So it is opposite to junction field effect transistors. So coming to the making of an Mosfet, as we have previously said, an NPN Mosfet is basically and an n channel creation, of n channel, and the gate is basically a metal. We have a dielectric, which is a SiO2, an oxide. We have a semiconductor, which is a p-type, and we have a positive gate voltage. So in the depletion region, if you come to the depletion region of Mosfet, so in the depletion region, the P for an n-channel Mosfet, the number of holes is less than the acceptor impurities, and whereas P is greater than the number of electrons. Whereas in case of the inversion region, the N is greater than P for an N channel. This actually becomes exactly opposite for an PN type. So if you draw a table with an NPN and compare it with PNP, so for the inversion region, for an NPN, the N is greater than P. For a PNP, it's P is greater than N. Where for depletion region, for an NPN, P is less than Na, and P is greater than N. For a PNP, N is less than Nd, and N is greater than P. Now, the contact potential or the built-in potential phi B is the difference between the Fermi level, intrinsic Fermi level EFI minus the Fermi level due to p doping EFP, and the surface potential on the other hand is EFI on the surface plus S minus EFI on the bulk. So when N channel is created, electrons are pushed to the surface. So consider when N channel created, the electrons are pushed to the surface. And we can have the relationship number of surface electrons is equal to surface Ni into exponential E S minus EB by KT, and this leads to something called a band bending. Due to this, and the relationship between surface potential and depletion width phi S is equal to ENA WT square by 2 epsilon 0 epsilon r. So a strong inversion will be a particular case of inversion when ns is equal to na. So you can say that when ns is equal to na, we can have a strong inversion. So by strong inversion we mean that the surface is as strongly n-type as the bulk is p-type. Surface is as strongly n-type as the bulk is p-type. And we can say that the surface potential will be equal to twice of the built-in potential, and will be equal to 2 kT log of Na by Ni. So if you would like to find out the n-channel width and the strong inversion, so the channel width at 100 strong inversion so that will be given as x is equal to Wm bracket root 2 minus 1 divided by root 2, where Wm is the depletion width, depletion width.